Here we have Module 6C. Now that we know how to do psychrometric charts, or how to use psychrometric charts, we'll do some processes with them, such as cooling and reheating of air-water mixtures and mixing of airstreams, and do some calculations using energy balances and mass balances with data from the psychrometric chart. Remember, for air-water systems, we have a cooling system will often occur in the evaporator of a standard refrigeration vapor compression unit. And so this would be an evaporator. And what happens in the evaporator is you bring air in, humid air, and as you start to cool it, it often reaches its dew point. And once it reaches its dew point, liquid starts to come out on the coils of the heat exchanger and comes out as a liquid. Typically this liquid is as low a temperature as the lowest temperature of the air coming out. So I'm going to put TL. Approximately T2 often I'll make that assumption. So, and the balances that we need to do are balances on the air. The air in equals the air out. On the water coming in with the humid air, has some water in it, is equal to the liquid water coming out plus the water coming out with the often saturated air leaving the evaporator. Let's take, for example, we have air at 27 degrees C and 60% relative humidity and want to cool it to 10 degrees C. Now for 4 tons of cooling, we want to determine the mass, the volumetric flows of the entering air, and the mass flow rate of the condensate, that liquid condensate that's coming out. So how do we start this problem? Here I've sketched a psychrometric chart a little bit for you. You have temperature, and you have omega, the absolute humidity, and relative humidity lines. Here's, say, 90, 80, 70, 60. Let's see, 90, 80, 70, 60. Go down to 60% relative humidity and 27 degrees. And that's our point 1. That'd be state 1 coming into the evaporator. And we'd cool it. We'd cool that air at constant absolute humidity, because there's no reason for the amount of water in the air to change until it becomes saturated. When it reaches its dew point, this is the dew point right here, then we'll have to follow the saturation line, and as we follow the saturation line, water drops out. And so the omega, or the amount of water in the air, the absolute amount of water in the air, drops until we get to the final outlet temperature, which was specified at 10 degrees C. So that's kind of the path that you typically take: cool to saturation and then follow the saturation line down to the final temperature. And that's for humid air, such as we have along the Gulf Coast. Now, first of all, air is cooled at constant humidity to its dew point, and then the process follows the saturation curve, as I mentioned before. Now we need to specify the exhaust relative humidity as 100%, because once it reaches the saturation, it stays saturated as long as there's air and water in contact together. And as you continue to cool it, it cools along the saturation line, so the exhaust relative humidity will be 100%. And we'll assume that the outlet temperature, T2, which we specified as 10 degrees, is the same as the outlet liquid temperature, which is coming off the coils of the evaporator. What I'll do now is specify some states. Let's take a basis of mass flow of air as 1 kilogram per second of just dry air. 1 kilogram of dry air per second, but of course we have the water coming in with that air. Next thing we'll do is set up a property process table, and what you have is the initial temperature, 27 and 60. This was specified. We can find all the other properties: the absolute humidity, or the humidity ratio it's often called. The enthalpy you can read from the psychrometric chart, if you recall, the enthalpy lines came, here's our point, the enthalpy lines run at this sort of angle like so, and that's where you'd read an enthalpy of 61.5. And then the volume lines are something like so, and if we found our volume of our entering air, it's 0.868, and that's meters cubed of the mixture per kilogram of air. That allows us to eventually calculate our mass flow rate from the volume flow rate of the air. Typically air is specified in volumetric flow rates, cubic feet per minute or meters cubed per minute or liters per minute. State 2, as we said, was 100% relative humidity. It's saturated. We can find the H at state 2, and that will be 29. And then state the liquid coming out of the evaporator. Let me draw a little sketch here. Here's the air coming in, air coming out, and then the condensate forms in little drops. And condensate comes out here. And we said that was going to be 10 degrees for the liquid condensate. And we get the data for that, what we'll call the liquid, from the steam tables for a saturated liquid at, that would be HF at 10 degrees C. Comes out to 41.9 kilojoules per kilogram. This is the psychrometric chart is designed to be consistent in terms of reference state with the steam tables. So next we have to do our balances, and first we'll do our balance on air. That's kind of trivial. The mass flow of the air, this is just the air in the mixture, in the air-water mixture stream. Mass flow of air in equals mass flow of air out. The water balance is the mass flow of air times the absolute humidity, and remember that was kilograms of water, H2O, per kilogram of just air. Is this omega is equal to the same thing going out, the mass flow of the air times omega 2 plus the mass flow of our condensate. This allows us to calculate the mass flow of the condensate by difference. And we took as our basis 1 kilogram per second of air. So we'd have leaving the condenser, or I'm sorry, actually that's evaporator for Freon. The Freon's evaporating, or the refrigerant is evaporating. But the air, the water in the air is condensing out, and the rest of the air comes out here, saturated air. That's very humid air. And then the condensate comes out as a liquid from your evaporator. You'll find one of these in your hall closet or in the attic, and you've got to be very careful to get that water away from your house to drain to the outside. Sometimes mold will grow inside of there and clog up the little pipe that takes that out, so you've got to be very careful that you don't let that leak into your house. While I'm on the subject, we need to make sure, this concept of a driving force for a heat exchanger, you need to make sure that there's a delta T between the coldest air, which would be over here. There's some driving force for heat transfer, so the R134A must be, let's see, we said this was 10 degrees C. So the R134A must be less than 10 degrees C by some amount that allows for the heat transfer. So we make it maybe 5 degrees C or 0 degrees C so that we can draw that heat out of the air. That's an important concept, that driving force, or delta T, for minimum delta T for heat transfer. Now the energy balance is mass flow of the air times its enthalpy. And this enthalpy represents the enthalpy of the air enthalpy of the mixture per kilogram of air. And again, the H2, Ma2, and remember Ma1 equals Ma2. It's equal to mass of the liquid times its H plus Q. Now we can calculate that Q is going from the air and into the Freon. That's Q dot, let's call it. So if we put the numbers in, we find out that for our 1 kilogram per second of air, we need 32 kilowatts. That's actually quite a large amount of air. quite a large amount of cooling if we had 1 kilogram per second. Now, the Q that's required turns out to be only 4 tons, and this is a conversion factor to go from tons of refrigeration. Remember what a ton is? A ton is 200 BTUs per minute. If you do the conversion, you'll find that 4 tons times 3.52 is a conversion factor, kilowatts per ton. 13.06 kilowatts of cooling is all we need. So we got this amount for 1 kilogram per second of air. So we really don't need that much air, and we can scale it at this point and find that our mass required, if we ratio it out, comes out to only 0.435 kilograms per second. Next, the mass of the liquid will scale according to the same ratio, this 14 divided by 32. Remember, this is the mass of the air we actually need, and this is the mass of the air. Actually, this is the Q actual, and this is the Q for our basis of 1 kilogram per second. So if we ratio those out, we should be able to find the amount of water that's actually flowing out of this process. So our amount of water comes out to 0.00252 kilograms per second. And if we scale that up, we find that's about 2 gallons per hour. So typical, this is a 4-ton unit, so 4-ton unit is fairly typical for a 3-bedroom house. So if you're cooling and taking out 2 gallons per hour, you definitely want to get that away from your house and not leaking anywhere. So there are a fair amount of condensate that you'll have, particularly in along the Gulf Coast where the air is fairly humid. If we calculate the volume flow of air that we're cooling in this evaporator, we scale our 0.435 kilograms of air per second times the volume that we found at state 1, 0.868 meters cubed per kilogram, comes out to 0.378 meters cubed per second, or 800 feet cubed per minute, or 800 CFM. And often you'll see your fans for your evaporator specified in CFM. So let's suppose next thing we want to do is, instead of putting saturated air into our house, we reheat it to 20 degrees C, so that we're not putting in this muggy, very humid air directly into the house. And sometimes that's done. Often you'll just mix it with the air already in the house, and that'll keep the relative humidity down. But remember, at state 2, the relative humidity was 100%. So if we want it to be a little more comfortable, what we'll do is reheat it. Now, when we do reheat it, we find out that the amount of water in the air won't change. We've taken this liquid out as condensate here, but from state 2 to state 3, there won't be any change in the amount of water in the air, because now we're adding heat to it, and it can hold more water, so the absolute humidity won't change. So omega 2 equals omega 3, and all we have to do is calculate H3. And if we reheat it to 20 degrees, we find that from the psychrometric chart, H3 is approximately 39 and relative humidity is approximately 50%. Let me show you how that whole process would look on the psychrometric chart. Here's your psychrometric chart. Something like that. We started with our air here at state 1. We cooled it to saturation, cooled it down to 10 degrees along the saturation line, and now we're at we had omega 1, now we're at omega 2, which is equal to omega 3, and we'll reheat it back along the to 20 degrees, back along a constant absolute humidity line to state 3. So this will be state 1, state 2, and state 3, and I think you'll find that if we go up to 20 degrees, the relative humidity there will be approximately 50%. And the enthalpy, if you read the enthalpy at state 3, that comes out to 39 or so kilojoules per kilogram of air. From there, it's fairly simple matter to calculate the QH that you have to put in. QH would be the mass flow of the air times H3 minus H2, give us the Q that we'd have to put into that air. Now let's look at another type of process when we're mixing air streams together. If we mix air streams together, you can have a couple of situations. Either the air will mix and won't be saturated when it's mixed, and you'll just have state 1 plus state 2 and state 3 of just air. Make this air 1, air 2, and air 3. Or you may have such a case that when you mix them, they form a saturated or a supersaturated mixture, which will cause water to condense and you'll have liquid coming out. This is actually what happens in a rainstorm when you have a warm, humid air mixing with cold air. You can have a front that causes, when those air streams mix, the cooler air can't hold the water anymore. It becomes saturated or supersaturated, and you'll have a thunderstorm. So mixing of air streams is important beyond just what happens in your house. Let's go ahead and show the equations that we'll use to describe it. First, we have the air balance, we have the water balance, and we have the energy balance. So it's fairly straightforward, very similar to what we did with the evaporator earlier. Let's take, for example, we'll mix 1 kilogram of air from state 1 above with 1 kilogram of air from state 2 for the problem we just solved. What's the temperature and humidity of the resulting mixture? So we have 27 degrees and 60%, 10 degrees and saturated. What happens at state 3? So first we'll do the air balance. 1 plus 1 equals the mass of 3. The mass of the water, 1 times its absolute humidity plus 1 times the second state's absolute humidity equals 2 times the final absolute humidity, assuming no condensate, no liquid from that mixture. And I'll show you how to tell in just a minute from the psychrometric chart if you're going to have liquid forming. And so the energy balance comes out to allow you to solve for H3, and H3 is 45.25. And so what you do is find it from the psychrometric chart. Draw it for you. Here we had state 1, 27 degrees and 60% relative humidity. State 2 was 10 degrees and saturated along the saturated line. So when you mix them, the resulting mixture is going to fall on the line between those two. Now I gave you the data we solved from the energy balance and the mass balance, but you can also do that on what we call a tie line. Our resulting mixture will be halfway in between, and then you can read off the temperature and the other properties, so on and so forth. I believe the enthalpy we said was 45, and the omega was 0.0104. So let me show you a little trick called the inverse lever rule, and that's for 2D graphs with specific properties, and this works for more than just psychrometric charts. But basically what it says that if you have two things that you're mixing and they have properties A and B, in this case we have temperature and omega, if you mix the two together, let's say we had mostly that they're going to fall on the line between state 1 and state 2. The mixture will fall on the line between state 1 and state 2. Well, it turns out that if it's mostly stream 1, if the mass is mostly stream 1, let's go back. If the mass is mostly stream 1, then it's going to fall close to property 1. And so the length from state 2 to state 1 will be very long. And so the length from state 2 to state 1 is proportional to the mass of 1. And if it's mostly state 2, if it's mostly state 1 again, then the length of this distance from state 1 to the mixture will be shorter, and that'll be proportional. So they call it the inverse lever rule. We call it the inverse lever rule because L1 from 2 to 1 is more proportional to the mass of mixture 1, and L2, the shorter distance, will be proportional to the smaller mass. So it's a handy way. If you took out a ruler, you could actually find, and you knew that stream 1 and stream 2 mixed, and say that it landed here for the final properties, you could use that information to find distance proportional to the mass of 1 and distance proportional to the mass of 2, and ratio those two out and find the mass of each stream that was mixed. Let's take an example. Relative humidity of 90%, 31 degree air. 1 kilogram is mixed with 10 degree saturated air. What's the state of the resulting mixture? Here's our diagram. And what we do is we draw it on the psychrometric chart. And when you do, let's see, state 1 was this very saturated humid air. Well, almost saturated. Let's see, it was 90% relative humidity and 31 degrees. So let's put it in a little bit. 31 degrees and 90%. Here's 90%. 31 degrees, fairly warm air, is mixed with 10 degree saturated air. This was I talking about earlier. If we mix them 1 and 1, 50%, try to draw that, 50%, then the mixture would fall, well, this distance would be proportional to stream 1, and this distance would be proportional to mass of stream 2, and you would find that you'd land halfway in between, since it's 50-50 mixture, 1 kilogram of one, 1 kilogram of the other. And notice that this is our saturated line of 100%. If when you mix the two together you wind up outside the saturated region, or outside at a what would be greater than 110%, we call that supersaturated. And of course it would have to condense to get back to saturation, so you'd have to drop out this amount of water here, this delta omega, to get back to saturation, and you would have dew forming or rain or some form of precipitation. So let's go ahead on and calculate. We'd have omega A1. This is going to fall on my chart, but you get the idea. There's your data from state 1, your data from state 2. The mass of the air combined is 2, 1 plus 1. And we can calculate omega 3. And without having to do it graphically, we could do it by the energy balance and the mass balances. And here we neglected H of the liquid above. But if we assumed water condensed to form a saturated mixture at that H3 of 63, T liquid equal to T3, then we could calculate that omega 3 would be approximately 0.0163. And the mass of the liquid that we removed would be this difference, or what I showed you on the chart earlier, that delta omega. Revise our energy balance and come up with the final H3. So it's a little bit complicated to do these calculations when the water drops out of it. Okay, let's look at cooling. We looked at cooling at constant specific humidity, and you recall, and it's just reviewing here what we've done. Here's our psychrometric chart. We take a humid mixture and we cool it at constant specific humidity, constant absolute humidity, and then once it reaches saturation, it cools along the saturated curve. We looked at reheating, and that's once you have this mixture cooled down, cooled along the saturated curve, but now it's very humid and you don't want to put it in your house too humid, so often you'll have systems that reheat the air again at constant specific humidity or constant absolute humidity, which lowers the relative humidity from 100% here to maybe, I don't know, 60 or 50 or some more comfortable relative humidity. And we looked at mixing of Airstreams, did balances on air, energy, and water, and use of the lever rule to obtain mixture properties, and talked a little bit about supersaturated mixtures. And that was pretty much it. For homework, take a look at Chapter 14 and work problems 69, 71, 82, and 105. And that should give you a pretty good feel of the types of problems that you'd encounter on a fairly good introduction to psychrometrics that we've done here.